This morning, I'm going to share with you some of the work that we have been doing in the past few years. I try to be simple with regards to some of the detailed findings that we have gathered. Sorry for that. The topic that we are interested in is how to recognize spatial orientation. In other words, you are all now sitting comfortably in the room, but how do you recognize the orientation? And this happens in different conditions. For example, if you happen to be in Italy and have a chance to go to the top of the Leaning Tower, you will know that your orientation is not upright. Similarly, when we conduct exercise or go to the theme park, then the spatial orientation will be disturbed. In literature, we found that the spatial orientation is first being recognized by organs within the inner ear. Sensors in the inner ear perceive the information and pass to the brainstem and subsequently to higher centers of the brain. And these are being interpreted to give us the sense of orientation. And for today's presentation, I'm going to concentrate on how the information is being processed at the level of the brainstem, and particularly during postnatal development. The first question that we ask is, when in the course of postnatal development does spatial orientation first being registered in the brain? And if that is the case, what is the underlying cellular mechanism? The animal model that we use is rat. In rodents, they are able to assume from a side-down orientation to a head-up orientation within seconds. And the way to conduct the experiment is by putting the animal on an inclined plane in this side-down position, and then within seconds, the animal can be oriented. And we call this reflex the negative geotaxic reflex. It is a sensation for the detection of gravity. When we try to map the course of postnatal development, we find that in adult animal, the animal can achieve this within 4 seconds after being placed on this inclined plane. And yet, when we look into younger animal, we find that in very young animal, the animal takes a very long time to reorient itself. And even, for example, postnatal day 4, the animal took 60 seconds. And the critical point that we define is 20 seconds. So we take the fact that at postnatal day 7, the animal is able to reorient itself. So of course, this is an arbitrary definition, but this gives us the starting point. And what we argue is that when an animal is being placed in this orientation, the sensors in the inner ear, specifically the otoliths in the inner ear, are being activated, and the hair cells, when they're activated, information will pass to the brain so the animal can reorient. So the maturation may take place there. So we use that as a starting point. Then we argue the information comes from the inner ear based on the findings that if we destroy the inner ear, we find that the animal will remain indefinitely in that orientation. And that proves that the ability of the animal to orient comes from the receptors in the inner ear. Next, we conduct some experiment using immunohistochemistry using C-force expression, which is an activity marker for neurons in the brain. And the stimulus that we use is we put an animal, alert animal, on a platform, and we have this sidewise stimulation. We move the animal along this horizontal axis, and we map the neurons being activated in the brain by looking at the C-force expression. And we find that at postnatal day 7, the neurons in the brainstem, specifically in the vestibular nucleus, start to express C-force. And when we look at postnatal day 6 animal, nothing has happened. And if we quantify the result, we find that the vertical bars indicate the number of neurons expressing C4s. At postnatal day 7, a significant number of neurons in the brainstem in the vestibular nucleus express C4s, but not at P6. In other words, this provides us with the cellular basis that it is the neurons in the brainstem that detect the orientation and pass the information to higher centers. If we try to look at the cellular mechanism, we would like to look at the contact between the afferent input and at the brainstem. When we look at the literature, we recognize that the transmission is glutamate. So we use glutamate as the starting point. And this is a schematic diagram that I have borrowed from some published work, from some review article, that at the polysyllabic end of this glutaminergic synapse, both NMDA receptor and AMPA receptor express. And everyone knows about that. And we have conducted experiments to show that functionally activated neurons with the expression of C4s co-express AMPA receptor and NMDA receptor, just as a control. In literature, we also recognize that for immature synapse, for glutaminergic synapse, the polysyllabic membrane, they do not express AMPA receptor. They only express NMDA receptor. And this is the case in the cortex and also in the hippocampus during the course of postnatal development. So we would like to ask whether this also exists in the brainstem. And now we change the experimental paradigm by using in vitro electrophysiological recording. The technique that we use is whole cell patch clamp. We prepare brain slice and then we patch the cell. And the stimulus that we use is paired stimulation. We deliver a stimulus to the afferent fiber and we also depolarize the cell. And this is one piece of data. Horizontal axis is time, vertical is the amplitude of the response. And here we find that at postnatal day 7, basically we could not observe any response from the cell. If you use younger animal, for example, at postnatal day 5 and repeat the same experiment, interestingly, we find that cells start to display some response. And we describe this as long-lasting response. So the long-lasting response lasts for 40 seconds. So we call this long-term potentiation. We ask, what is the origin of such a long-term response? We use a peptide, an interference peptide, targeted at the CT end of the GluA1 receptor subunit. And we put this in the recording pipette. And we find that after we put this in the recording pipette, the response disappears. So this was the original response. After we put the interference peptide into the pipette, the response disappeared. And the response reappeared again if we put into a control peptide. It reappeared. So we argue that during the process, it is due to the insertion of the AMPA receptor into the polysyllabic membrane, and this caused the occurrence of this response. In other words, during the course of postnatal development, we proved that at around postnatal day 5, the animal is able to allow the AMPA receptors to insert into the polysyllabic membrane. And because of this response of the AMPA receptor, and this will cause the cell to be excited. In order to prove this, to see whether this is related to the reorientation observation that I have shown you just now, we conduct another experiment, and this time we conducted an in vivo experiment. We use a material called alphax, and we loaded NMDA receptor antagonist MK801 into the alphax so that the drug can release slowly into the underlying tissue, and we have this piece of biomaterial inserted at the top of the brainstem. So the whole idea is to perturb the system with drug. In order to ensure whether the drug is delivered to the tissue, we conducted also whole cell patch clamp experiment. And this is the control data, postnatal day from young age to adult. and the fielded bar is the NMDA component. We find that the NMDA component is very large in the control, but then after the treatment of MK801, the NMDA component starts to decrease. In other words, this is an effective delivery of drug into the brainstem. And what was the outcome? The outcome was that after the introduction of MK801 into the brainstem, particularly into the vestibular nucleus, we find that the emergence of negative geotaxis at posterior day 7 was delayed to posterior 11. In other words, if we block the response of the NMDA receptors in the vestibular neurons, we are able to postpone the emergence of the negative geotaxis. What about the drug, the interference peptide that we use? The interference peptide that we used was GluA1-CT, and it was able to block the expression of the LTP in the neuron. And now we use this again in the whole animal experiment, and we find that with the introduction of this drug, the whole process was also able to be delayed. In other words, we can link the whole process to the fact that the switching on of the circuitry actually is dependent on the insertion of AMPA receptor. And this is closely related to the expression of this gravity-sensitive behavior. Just now, we observed that by perturbing the system with either NMDA receptor antagonist or with AMPA receptor reagent, we are able to shift the curve to the right-hand side. We are able to delay the expression of the response. So we ask another question. Are we able to move the curve to the left-hand side? Are we able to accelerate the whole process, to speed up the whole process, so that the animal can recognize the orientation even at a younger age? We look at the brain. For any neurons in the brain, usually the neuron receives excitatory input via mostly glutaminergic synapse. At the same time, they also receive a break, the GABAergic synapse, which is an inhibitory input. So at any one time, neurons in the brain receives excitatory input and inhibitory input. And in the brainstem, we find that neurons also express GABA-A receptor as shown in this immunohistochemical data. So we use this as the benchmark and conduct experiment to see whether the GABA inhibitory receptor can affect the expression of the gravity-sensitive behavior. We all know that GABA transmission is inhibitory in nature. It serves as a brake. But in literature, we also find that GABA transmission in very young animals is excitatory in nature. So we performed the experiment to see whether in the system that we are using, whether the GABA transmission in very young animal is excitatory in nature or not. To conduct the experiment, we have to use a very difficult approach, whole cell patch clamp, but it is a perforated patch clamp experiment. The way to do the experiment was again to patch the cell, but we use gramazidine in the pipette so that pores can be made in this patch. And the whole idea is not to allow the flow of chloride ion across the membrane. In adult animal, we find that from here that the E-GABA is more negative than the resting potential, so this indicates that the GABAergic synapse is inhibitory in nature. We perform similar experiment in very young animal, and we find that the E-GABA becomes more positive than the resting potential. So what does that mean? Okay, I know many of you may not have the background of electrophysiology, so I try to make it simple. In other words, in this case, when the animal is very young, when we activate the GABA-A receptor on the cell membrane, this will cause the moving of the chloride out of the cell because of the concentration gradient. And in this case, this will cause depolarization of the membrane. Depolarization means that the membrane will become excited. In other words, by using in vitro electrophysiological experiment, we provide the evidence that in very young animal, if we are able to activate the GABA A receptor, we should be able to increase the excitability of the cell. But of course, this is not the case in adult animal, because in adult animal, if we activate the GABA A receptor on the membrane, the cell will be inhibited, will be stopped. So we go back to this experimental paradigm that I have described to you earlier. We use the negative geotaxis. This time, we use mucimol. I think we are all familiar with mucimol. Mucimol is a GABA A receptor agonist. And we load mucimol into the alphax, and again inserted the alphax into the surface of the brainstem. The whole idea is to slowly deliver mucimol into the brainstem. And the experimental outcome was similar to our expectation. With the introduction of mucimol at posterior day 1, we are able to shift the curve to the left-hand side. So we are able to accelerate the emergence of this response. So the summary is that GABA transmission in very young animal enhances excitability of the cell and triggers the expression of the behavior. We all know about BDNF. BDNF is a brain-derived neurotrophic factor. It is known to enhance the transmission of neurons. So we like to see whether BDNF plays any role in the phenomenon that we have observed just now. So this is a cartoon showing that BDNF, the receptor, can in turn activate the GABA transmission. So we conduct experiment to see whether if we deliver stimulus to this neuron, whether the GABA transmission will be affected, and subsequently whether this will affect the behavior. Again, we use whole cell PET clamp data. In control experiment, in the control situation, the magnitude of the response is depicted by the blue line. And after stimulation is being delivered, we find that the response becomes smaller. With the introduction of BDNF into the system, we find that after stimulus, the response depicted by red became bigger. In other words, the introduction of BDNF is able to enhance the responsiveness of the cell. And if this is the case, what will happen if we introduce BDNF into the alphax? We perform the experiment again, introducing BDNF into the alphax, and we find that the curve is also shifted to the left-hand side. In other words, at this juncture, we can make the conclusion that introduction of BDNF into the system is able to produce a bigger GABA current. When we compare this, the GABA current is bigger. And the bigger the GABA current, as what you have already gathered just now, in very young animal, when the GABA current becomes bigger, excitability occurs. And the excitability will accelerate the emergence of the response. So we come to the second summary of the talk, that BDNF is able to modulate the synaptic plasticity, and this will also affect the expression of the gravity-related behavior in very young animal. So now let me go to the final part of my talk. After observing all this cellular mechanism, that NMDA receptor, AMPA receptor are able to delay the responsiveness of the gravity-related reflex, GABA receptor, BDNF are able to shift it to accelerate the response. What about in our daily life? Right at the beginning of my talk, I mentioned about the ability of the animal to search in space, to walk around in maze. So I asked the question whether if we perturb the system in very young age, whether we are able to alter the spatial navigation behavior of the animal. This is a cartoon showing the experimental paradigm, spatial navigation. We use a dead reckoning test, a round table with many homes, and this is the home base for the rodent. We conduct the experiment first in the light and then the dark, and then we change the location of the home. So as the cartoon indicates, the chap will be confused in the various situations. So we use rodent for the experiment and see what will this happen to the rodent. The way to conduct the experiment was relatively simple. Animal search mainly for food. So we use this round table, and this is the home base of the animal, and we put the food on to the middle of the table. So what we have observed is that in the literature, in a paper published about 15 years ago, 1990, more than that, by hippocampus, when the animal comes out from the home base, it will take some time and then will take the food and then go back to the home base. But it takes the rat a long time to learn this. For adult rat, it usually takes the rat about 10 days for the training process. So this is not a very easy job for the student. With the destruction of the inner ear, we find that this is a mess. So this indicates that the inner ear also contributes to this navigation orientation. So we use the experiment, and then we use two experiment paradigm. One is to perturb the brainstem with MK801, NMDA receptor antagonist, and also in second experiment, we perturb the system with muscimol GABA receptor agonist. And if you look at the bottom diagram, this is the control, 10 days to learn. But with MK801, we found that the animal took almost 1 month to learn the technique. And for muscimol, it is quicker. Well, basically, we find that, well, this somehow delays and this accelerates. But this may have nothing to do with the gravity receptor experiment, because this is a new set of experiment. And first, when we look at this horizontal row, under the light condition, and this is the platform, this is the home base, animal comes out, and this is the outward path, the red is the homeward path. Horizontal axis is time. And we find that with the course of time, the animal comes out and then comes back. But with the perturbation of the system with the NMDA receptor antagonist or with the GABA receptor agonist, we find that the outward time was increased. And when we switch off the light, we find that the homework time was increased. In other words, by perturbing either the NMDA receptor in the system or the GABA receptor in the system, we are able to change the navigation time of the animal. And this is just some data for you to further appreciate. For example, horizontal axis in the light, sham control is like that, but if we perturb the system MK801 or muscimol, we find that there is a mess in these two systems. In other words, we are able to come up with the final summary that if we perturb either one of this system in very young animal, we are able to perturb the motor learning behavior of the animal. So the last piece of information that I will convey to you is that the acquisition of spatial navigation in rodents depends on the balance of glutamatergic transmission as well as GABAergic transmission in the brainstem. So with that, I would like to end my talk by introducing to you this cartoon. I'm working on spatial navigation. I try to map out the underlying mechanism. So the dream is that in the future, maybe we're able to come up with a system that can control our own GPS unit. Okay. Whether this will come true or not, I think let's dream about that. And of course, the work cannot be accomplished without funding from the Hong Kong government and also from the private foundation, and also contribution from collaborators in Canada, Yuteng Wang and also T.P. Wang. They provide the interference peptide, and also inputs from associates in Hong Kong. I have put their names in green, and those in asterisk are the current members of the group. And with that, I would like to end my presentation. And this is Hong Kong. My medical school is located here. So you are all welcome to come to visit me to the complex, medical complex of our university. Thank you very much.